This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 25, Electronic Spectroscopy. Section 25.1, the energy of electronic transitions. In this section, we will compare the energy of electronic transitions with the energy of vibrational, rotational, and translational transitions of atoms or of nuclei. So first, let's talk about the spacing between the energy levels. The spacings between energy levels depend on two factors. One, the mass of the particle of interest, whether it's an electron or a nucleus. There's a big difference. Two, the spacings, the energy spacings, depend on how much this particle is confined within a 0.1 angstrom range, or 1 angstrom, or 10 angstroms, or 1 centimeter. That makes a huge difference. 1 angstrom is 10 to the power negative 10 meters. 1 angstrom is 0.1 nanometers. So now if we know the mass of the particle of interest and how much this particle is confined, to what extent the particle is confined, we can estimate the order of magnitude of the energy spacings of the transitions. How? We'll use the particle in the box model. We will make it really simple. We will use this one-dimensional box, and we will confine the particle completely inside the box. And then we know the expression of the energy levels. It's n squared h squared over 8 ma squared. N is the quantum number. But now we're talking about transitions. Transitions occur between two different energy levels, the initial energy level and the final energy level. So if we take the difference, I want to say the difference is the energy of the transition. It's roughly or proportional to h squared over 8 ma squared. All right, again, this comes from the particle in the box model. Now we estimate h squared over 8. It's roughly 10 to the power negative 67 joule squared second squared. But also joule squared second squared is the same as joule times kilometer times meter squared. Well, how do I know this? Well, eventually we'll have to cancel the unit here and here so that this delta E is eventually in joule. All right, so the unit of this should cancel the unit of this ma squared. And also, if you do know 1 joule is 1 kilogram times meter squared per second squared, we can convert joule squared to this easily. Now we can convert joule to kilojoule per mole by multiplying this number by the Avogadro constant. Avogadro constant is 6.022 times 10 to the power 23, and then we convert joule to kilojoule, so we have another order of magnitude here. So these two numbers differ by 10 to the power of 20. So those are all just a rough estimate of the order of magnitude. Now let's look at the electronic transition, vibrational transition, rotational transition, and translation transition. The electronic transition involves electrons. The mass of an electron is roughly 10 to the power of negative 30. And now we'll talk about the vibrational, rotational, and translational transition of atoms or nuclei. The mass of a typical atom is 10 to the power of negative 26 kilogram. So if you compare the mass of electron and the mass of atom, they differ by 10,000, 10 to the power of 4. Now let's look at the range in space of the electrons and the atoms. In an electronic transition, the electrons can move roughly within 1 angstrom range, or several angstroms. So I'm going to just estimate this particle in the box model. The dimension of the box is roughly 1 angstrom here. Vibration. Vibrations usually involve the stretching of the bond or the change of the bond angle. In those cases, the position of the atoms move by roughly 0.1 angstroms, or in that order, okay, 0 point something angstroms, 0.2, 0.3. So I'm going to put 10 to the power of negative 11 meters here. Rotation. If you imagine the rotation of a simple HCl molecule, both H and chlorine move in a circle, and I want to say the diameter is roughly 1 angstrom. So I'm going to put this 1 angstrom here, or 10 to the power negative 10 meters. Translational transition of atoms. This is a little difficult to estimate. It really depends on the actual container that you use to confine the substance of interest. But I'm going to say, well, maybe we have a container in the size of 1, okay, in this case 1 millimeter. So you can say 1 centimeter or 1 decimeter. I'm just trying to give you a somehow reasonable number here. I'm just assuming you're looking at a very small container with a size of 1 millimeter. You can still see this container, all right? So it's still at the macroscopic level, all right? Now we're going to just estimate MA squared. We got this numbers. And then we can estimate delta E by using this equation. We get the order of magnitude. Now you can see delta E for electronic transition is 10 to the power of negative 17 joule. Vibrational, 10 to the power of negative 19. Rotational, 10 to the power of negative 21. Translational, 10 to the power of negative 35. But again, I want to emphasize here, I estimated a 10 to the power of negative 3 meter as the dimension of the box. But you could have a normal flask, and then it's going to be 10 to the power of negative 1 meters, and this 10 to the power of negative 32 will be 10 to the power of negative 28. Okay, and this will be 10 to the power of negative 39. Okay, again, I'm just trying to emphasize this. This is just a really rough estimate of the order of magnitude of the dimension of the container. It can be 1 decimeter, it can be 1 millimeter, or as long as you can kind of see it, you can actually see the container. All right. So in this case, we'll have anyway very small energy spacing. 10 to the power of negative 35, 10 to the power of negative 39. It's just negligible. If you convert it to kilojoule per mole, well, it's still negligible. It's 10 to the power of negative 15 kilojoule per mole, or 10 to the power of negative 19 kilojoule per mole, really small. However, if you convert this electronic energy spacing to kilojoule per mole, the number is large. It's 1,000 kilojoule per mole. It's in the same order of a strong chemical bond. For example, the chemical bond strength of nitrogen 2 is roughly 1,000 kilojoule per mole. The H2 bond strength is roughly, I think, 450 kilojoule per mole, roughly. Carbon hydrogen also roughly 400 kilojoule per mole. All right, and if you look at some ionic compound, for example, magnesium oxide, I think it's in the order of 1,000 kilojoule per mole. So this number is pretty large. Although this number looks small, but if you convert it to kilojoule per mole, you get a big number. That's why units are so important in chemistry. Now, vibrational energy spacing is 10 to the power of negative 19 joule, or roughly 10 kilojoule per mole. All right, so if you want to calculate the bond energy of a diatomic molecule accurately, you need to get this part and you need to get this part as well, because if you want to have an accuracy up to several kilojoule per mole, or maybe 10 kilojoule per mole, you need to include the vibrational energy of your molecule. Now, vibrational energy spacing is 10 to the power of negative 21 joule. After you convert it to kilojoule per mole, it's 0.1 kilojoule per mole. Finally, translational. This energy spacing is so small, mainly because we're talking about the translation in a macroscopic container with such a big dimension compared to angstroms. All right, so this is 10 million angstroms. All right, and this is 1 billion angstroms. And look at this energy spacing, A squared appears on the bottom, so that's why. I want to show you the qualitative comparison here. The energy spacing of electronic transition is roughly 100 times greater than the vibrational energy spacing. The vibrational energy spacing is roughly 100 times greater than the rotational energy spacing. The rotational energy spacing is so much greater than the translational energy spacing. Look at this, 1,000, 10, 0.1, and then really small. All right. So this two differ by 100. This two differ by 100. This two differ by, well, a lot. Units are important, so I'm going to show you the conversion of this energy spacing in other units. I'm going to just tabulate the electronic transition, vibrational transition, and rotational transition here, because the translational transition of the atoms or nuclei in a macroscopic container, however small it might be, even it's just a really tiny container of 1 millimeter dimension, you get tiny energy spacing. So we're going to just neglect the translational transition of the nuclei. So only this 3 columns, energy spacing. This time I'm going to give you a range. The energy spacing for the electronic transition is 120 to 1200 kilojoule per mole. Vibration usually between 1 to 50. Rotational transition usually between 0.01 to 0.5 kilojoule per mole. So you have the lower end, you have the upper limit over here. Now we'll convert kilojoule per mole to wave number. How do we do this? Well, you need to convert this kilojoule per mole to joule, and then Hc over lambda is this energy in joule, and the wave number is 1 over lambda, and then you can convert the energy in joule to the wave number. I'm going to use not the reciprocal meter, but the reciprocal centimeter here. It's just the most chemists are more familiar with this centimeter to the power of -1. It's also called 1 wave number. Okay, 1 wave per centimeter is called 1 wave number. 1 wave number is 1 wave per centimeter. 1 wave number means the wavelength of this wave is 1 centimeter. All right. So now let's look at this electronic wave number. It's 10,000 to 100,000. That means you can have you can put 10,000 to 100,000 waves within 1 centimeter. So the wavelength is 10 to the power of -5 to 10 to the power of -4 centimeters. The wave number of the vibrational transition is between 80 to 4,000. Well, that's why when you took the infrared spectrum of a organic or inorganic compound, you usually see a range between 200 to 4,000. So that's the typical range. But if you have a molecule composed of really heavy elements, sometimes you'll see wave numbers below 80. I cannot remember what's the vibrational wave number for potassium bromide. I think it's roughly 200. So if you have cesium iodide, I think its vibrational wave number is going to be much closer to the lower end, maybe 100. That's my guess. The rotational transition has even smaller wave number. It's between 0.1 to 40 waves per centimeter. So you have a fairly long wave here, as long as 1 centimeter. Okay, over here. So 0.8. That means you have wavelengths of roughly 1.2 centimeters. So now you can convert wave numbers to wavelengths by taking its reciprocal. So if you take the reciprocal of this, you'll get the wavelengths, which is 10 to the power of negative 5 to 10 to the power of negative 4 centimeter. All right, so we convert it to nanometer here, and it's between 100 to 1,000 nanometers. So this is in the UV range. This is in the infrared range. In the middle, you have visible light. Vibrational transition. The wavelength is between 2.5 and 125 micrometers. Rotational wavelength, it's between 0.025. That's from this 40, the reciprocal of 40, and the reciprocal of 0.8 is 1.25 centimeters. So this is the wavelength for the rotational transition. Radiation type. From 100 to 1,000, typically it's UV-vis, but it's possible for you to observe near IR transition. How is that possible? Just look at the hydrogen atom. If you have electronic transitions from 3 to 2, 4 to 2, 5 to 2, 6 to 2, you observe visible light. But then if you just imagine a transition from 4 to 3, that's infrared. Okay, 4 to 3, that's infrared. 5 to 4, that's infrared. But if you look at the Lyman series from 2 to 1, 3 to 1, well, that's UV, ultraviolet light. Vibrational infrared, that's why we use infrared or Raman spectra to look at inorganic and organic compounds. Rotational transition, well, it's in the range of microwave. It's in the range of microwave. So if you have a microwave, when you heat food, you are actually making the water molecules rotate faster. And also, you are exciting some small wave number vibrations in large molecules. So in your food, there's typically protein, polysaccharides, those kind of polymers, and you have many vibration modes. Some vibrations have really small wave numbers, so it's also possible for you to use microwave to excite those vibration modes with small wave numbers as well. Finally, I want to mention this. In the real world, you don't usually see pure electronic transition, pure vibrational transition, or even pure rotational transition. You observe the coupling of electronic transition and vibrational transition. So they may occur at the same time. And also the vibrational transition is coupled with a rotational transition. So this is really complicated. So when a molecule absorbs a photon, it's possible that this molecule undergoes an electronic transition and a vibrational transition and a rotational transition at the same time. What about translational transitions? Well, they may occur as well. It's just we don't care. We don't care about the translational transitions of atoms or molecules because that requires just a tiny amount of energy. So, and because of the huge gap between electronic transition and rotational transition, they usually differ by a factor of 10,000. So when we are looking at the coupling, at most we look at the coupling between electronic and vibrational transitions. Okay, they differ by a factor of 100. And we look at the coupling between vibrational and rotational transitions. They also differ by a factor of 100. So we look at those if we are really careful, trying to get very accurate result or making accurate predictions. But I don't think any scientists seriously look at the electronic transition and rotational transition together because they differ by a factor of 10,000. So that's too much.